very, very much for this warm welcome, and it's truly my honor to be here addressing the RFIC conference. And it's kind of an exciting time in 2025 as we look forward to the next 5 years, setting the stage for 6G, and then kind of what's coming in the next decade. So it's really my kind of joy to be speaking to you about how I view the kind of future of wireless communications across a wide range of applications and technologies. One little thing about Qualcomm, it's interesting where obviously Quality Communications is the name of the company, but at the same time we've really expanded as well into how different areas of communications interact with low-power computing or even edge AI now. So a huge expansion in the company's footprint from smartphones into connected vehicles, augmented virtual reality, IoT, and a lot of other changing technologies. And one of the exciting things about being in wireless is that as wireless changes, it moves along with all of these other technologies. And I think what's exciting then is these new areas of research are about this intersection of how does, for example, cloud computing play with wireless, as we look at the role of AI in wireless, as we look at the role of sensing in wireless. So when we take that broader view of that evolution from 1G to 2G, all the way to 4G, 5G, 6G, it's about that different perspective, putting them all together, and this kind of understanding that the role of us as wireless research engineers is to how do we look at the mixture of evolution and revolution, getting the best ideas and at the same time bringing those into the most compelling applications and putting it together. So kind of our broad view then is this role of AI. We love data centers. Data centers are great. At the same time, value is really created at the edge. Whether we're talking about a smarter school, a better factory, a more effective hospital, all of those different technologies are going to be happening at the edge. It's where the people are. It's where a lot of that value gets created. And all of that AI is going to be connected via wireless. So that's the kind of key role of RF. The role of plugging things in at the endpoints is becoming less and less relevant every single day. So as we look towards this future of designing 6G, it's about understanding that we're really designing for this connected computing, and how are the different wireless technologies then evolving alongside to bring this value. So then when we look at kind of the role of 5G, a lot of people ask me, hey, how much has 5G been deployed? And so here we are at that kind of halfway point between 5G and 6G, the 2025 checkpoint. And it's amazing how many operators globally have already invested in 5G. And even just this week, in Europe, we were kicking off the 6G RAN study item at the plenary meeting, kind of getting stuff ready for that next generation. But it's truly about recognizing that the wireless footprint has really expanded. So the surface area of wireless is getting bigger every year. And even seeing the number of awards given tonight, as well as I was walking through a mini history lesson before my talk about the different technologies on display, it's amazing to think of where we've come, since 1940s, all the way through the last century into the last 25 years of this century, and kind of recognizing that wireless is going to keep evolving. It's going to keep intersecting with new applications and new services. A great example was the X85 product that we recently announced, all the way up to 12.5 gigabits per second, combining both millimeter wave and sub-6 gigahertz, and then also bringing in AI into the device itself. So not only are we going to have smarter networks, but we're going to have smarter devices. And we're also going to use new algorithms to have that end-to-end performance improvement. As we look at example then, some of the key components of it, going all the way up to 400 megahertz of bandwidth on the downlink, all the way up to 1024 QAM, and in an uplink speed of 3.7 gigabits per second. It's certainly not lost on us that the importance of improving uplink, improving that power-constrained transmit efficiency is incredibly important for how we're looking at that communications future. The need to make sure the improvements are happening when there's a power constraint, an energy constraint, a size constraint, and making sure we're delivering that compelling technologies. The other one is how can we use AI, for example, to improve beamforming? How can we use it to improve the channel state feedback between the network and the device? As we look at more MIMO schemes, getting that higher and higher spectral efficiency requires more interaction between the network and the device. So this is a great example where we're bringing AI, not only in the releases 18 and 19 standard, setting the stage for 6G, but also into the device itself in terms of new algorithms. And this is our millimeter wave antenna module, where if we're looking at bands, for example, 26 gigahertz, 28 gigahertz. And so this is an example where we've continually evolved this generation after generation as part of this 5G journey. So with 5G originally launched commercially just around 2019, 2020, we've continued to evolve and drive that millimeter wave improvements because of that huge amount of capacity it offers. Even at the recent Super Bowl, there was a lot of traffic was shared over 5G millimeter wave itself because of that ability to carry huge amounts of traffic node. And even there was a lot of operators saying, hey, you might want to turn off your Wi-Fi to get better performance because of the amount of capacity now available in cellular, and then the key role of millimeter wave in driving that hotspot performance. So as we look longer term towards 6G, there's a lot of questions around, well, what are the most important use cases? What is the capacity needs into that 6G 2030 era? And this is something where we look at the reality then of the role of uplink, the role of augmented and virtual reality, also the role of AI, not only as a tool that all of us as engineers are going to use, but also AI traffic itself. So the role of, as we move from large language models to video models to a more immersive communications world, that's all going to need a lot of communication. The role of sensors at the edge of the network is also going to need a lot of communication. So in our view, there's going to be a lot of capacity and data rate growth needs emanating not only from the network to the device, but also from the device to the network. So one could argue we're kind of in that peak amount now of download streaming, whether it's in entertainment or a Teams or Zoom call, but also that fact then there's going to be a lot more data generated at the edge of the network. And that's really going to transform how we're looking at that continued need for wireless communications. And this is something where we look, for example, at augmented virtual reality. That's been a really important area for Qualcomm's expansion, recognizing that that multimedia technologies that were in your smartphone has a lot of applicability to the very fast changing world of augmented and virtual reality. As part of that, we're always looking at what are the most important ways then that the wireless communications aspect, whether it's 5G from the network to your phone or Wi-Fi from the phone to the XR headset, what is that future on the human computing interface? And then also the role of digital twins and RF sensing. So whether it's a smarter factory or bringing more value to enterprise, the role of communications and computing are becoming more and more intertwined. So when we look then longer term at what are the 6G targets, we kind of joke around at Qualcomm since we've been in the G business for many, many decades now, but it's something where, you know, the good stuff gets 10 times better, the bad stuff gets 10 times smaller. But at the same time, it's really about what are the right vectors, what are the directions we can push harder in. So how can we improve latency? How can we improve coverage? If we look at cellular, the fundamental value proposition is coverage. Are you covered? Do you have a signal? Are you able to close the control channels, the data channels, go through all of the procedures as efficiently as possible? So then that role of uplink communications is also really important. So in our view, as we look to that 6G era, the constrained optimization of very power and energy efficient communications from networks to devices and back is going to become more important than ever. So just to level set on the time frame, so I mentioned we're about halfway through the 5G commercial journey in the sense it was deployed in 2020. And the interesting thing then, as we look at 6G, the R&D's been going on for a long time, and the standardization is just beginning in earnest this year. So right now in 2025, the 6G standards work is beginning. And that's going to pivot into this Release 20 study item, setting the stage for Release 21 is the work item that actually creates the first 6G specification. And that work item in Release 21 is what sets the stage then for that 6G commercial deployment in the 2030 timeframe. Now the interesting thing, every device, so many of them are multi-mode. We talk of 4G, 5G, Wi-Fi, Bluetooth, UWB, all of them within the device. And as we move to the 6G era, it's also then important about how do we make sure that this technology evolution and expansion is cost effective. So how do we make sure that we're moving things in the right direction and working across all of the different frequency bands? And so this is something where we're looking at not only continuing to improve millimeter wave, but then also what are some new technologies we can bring into that mid-band spectrum. For example, 3 to 6 to 7 to 8 gigahertz. And then also, what can we do below 1 gigahertz, between 1 and 2 gigahertz, the FDD bands? So the role then of all of these different spectrum bands is incredibly important. And as we look at different applications and different scenarios, we're looking at what's the most important and most cost-effective way to achieve that performance target in a given band. So one of the things we talk about a little bit is that distance from Shannon capacity. So in an AWGN, so a classic link without fading, the channel codes are getting quite close to capacity. What we're showing here, though, is in a 20 megahertz system with 4x4 MIMO, and link adaptation, where there's some mobility, we're still far away from that limit. There's still a huge amount of benefit to be achieved by improving the communications and the feedback and the mechanisms to get that spectral efficiency improvement. So this is just something where that continued evaluation, where are we today, how can we improve things, and what are the different components that come together to achieve that. So one example is, for example, in these lower band FDD, our calculations show we can achieve between 50 and 70% gain due to better spectrum occupancy, better downlink MIMO, uplink transmit and receive power management, and even continuing to improve modulations and shaping, and looking at that waveform design. And it's also something where we're looking at this movement from massive MIMO into giga MIMO. So what are the interesting things we can do when we look at the infrastructure side, the base station side, the sheer number of antennas that we're able to support, the number of baseband streams, basically the narrowness of the beams, and at the same time, the ability to spatially resolve them for capacity gains. The ability to harness time, frequency, and space is going to be really, really important. It's going to be key to this next evolution in this TDD bands. And it's one of the reasons then we're focusing on how can we design a system not only on downlink but also on uplink. What are the techniques we do to bring together that overall performance benefit? So when we look then, it's about understanding from a technique standpoint, from a frequency band standpoint, and then also from a global standpoint. So we saw how many people are at this conference today from all these different countries, different regions. Well, the same thing in spectrum. From the WRC, we just had WRC 23. We're setting the stage for WRC 27. A lot of focus then with regulators worldwide to make spectrum available for these communications. So this is something where we're working targeted spectrum bands in each region, saying what's the best way to bring more spectrum into use? What is the coexistence, whether it's between satellite and terrestrial or between an incumbent and a new entrant? And even as we're looking at the role of Wi-Fi, the role of cellular, the role of different types of devices. So the spectrum landscape is incredibly important because it's what unlocks that capacity for all of these different systems. And one of the kind of ways that we look at capacity then is a lot of extensive measurements. We build out our own over-the-air networks well ahead of the standard. So we have a 6G test bed in San Diego where, for example, we're already looking at sub-band full duplex. We're looking at new techniques, for example, at 13 gigahertz and 7.5 gigahertz. So what are the ways we can use these to bring higher capacity? So as we know, if we're doubling the frequency, we're having the wavelength, and we start getting then 4 times more antenna elements. And can we prove our ability then to harness that in a cellular network when there's mobility, when there's multiple people, when we're doing OFDM, multi-user MIMO, all of these different techniques. So it's incredibly important then, all of the constituent research, how it gets stacked together to deliver these gains. Similarly, we look at continued evolution of millimeter wave. The amount of bandwidth that millimeter wave brought into 5G is huge. It's a huge amount of spectrum, and it's a very, very high data rate communication links. So there's a lot of important work continuing to push forward on millimeter wave improvements. Not only improving 5G millimeter wave, but looking at what are some techniques we can do in a 6G context, making sure that we're looking end-to-end across all of the possibilities to have this improvement in the spectral efficiency, in coverage and capacity, and then also looking at co-design across different spectrum bands, low bands, medium bands, high bands. A good example of that high band research is our R&D in sub-terahertz. We obviously don't think that 140 gigahertz is going to replace, sub-6 gigahertz spectrum in terms of wide area cellular, but at the same time, the amount of communications bandwidth at sub-terahertz and the applications are really interesting. So we've been doing a lot of R&D into, for example, connecting data centers or looking at different applications for RF sensing. And what are the different experiments we're doing on our research teams to put together these technologies. When we started to look then also at satellite, it was interesting to see this a space debris comment in a plenary session here earlier. And it is interesting where satellites were like a big deal. Qualcomm, for example, was a key contributor to the Globalstar system many, many years ago before I joined Qualcomm. And at the same time, satellite is becoming more important because of the surface area of wireless. So whether it's a container ship and logistics, or whether it's people who are unconnected, who are really needing that cellular connectivity and being able to leverage those satellite links. So that ability to design satellite systems was already brought into 5G. So in release 17 of 5G, we had non-terrestrial networking. As we look towards 6G, we're also then bringing in that technology and looking end-to-end at an evolved 5G, 6G non-terrestrial networking. And so our R&D testbed, we're working with other industry partners to showcase our ability to track the high Doppler movement of the LEO satellite and then also account for the link budget and delay. So the ability to have this non-terrestrial network be part of the overall communications infrastructure, I think it's really been shown in the last couple of years, this is an important and evolving sort of technology. So just as 5G brought it into the system, 6G is going to continue driving that forward. The other topic that's very interesting is sensing and communications. We have integrated sensing and communications where our ability then to have wideband signals where not only can we do ranging, but we can also look at sensing applications. And we can use wireless signals, and we can also improve the wireless performance by different types of sensors. So it's an interesting one. There's a study item topic in 3GP called Integrated Sensing and Communications, or ISAC. And it's about putting together these different technologies in creative ways. As I mentioned, this mixture of evolution and revolution. So some of our advanced technology demonstrations were about sensing enhanced communications or aerial drone detection, where we were flying a drone around San Diego and using our signals from our test base station to track the location of that, leveraging, for example, the Doppler signatures of the different quadcopter antenna rotors. So it's something where when we look at sensing, it's about recognizing that sensing and communications are becoming more intertwined, just as communications and compute are becoming more intertwined. So then when we take a step back and we look at that 6G generation, that 2030 timeline, it's about recognizing that all of us globally are becoming more and more connected. It's about recognizing also that it's not about just connecting people to their television streaming on their phone, but it's also about reality of all of these different types of industries are becoming more connected. So the surface area of wireless is truly getting larger. And so this set of use cases being addressed in that 5G, 6G evolution is only getting larger. And at the same time, we have to make sure as an industry that we're bringing together the techniques in the most cost-effective way. What I kind of love about this conference here today is how many people are a mixture across industry and academia and the next generation of students. And so at Qualcomm, we're happy to have all of these different technology demonstrations publicly visible, and we're always happy to follow. We have quite a few Qualcomm attendees participating over the next few days, but we're always happy to share interactions and understand questions from different students and faculty. And so this is just some of our public demonstrations talking through some of our technology challenges as we see what lies on the road ahead from an R&D standpoint. So thank you again very much for the opportunity to address the audience here, and I hope you enjoy the rest of your conference. Thank you.